In this section, we're going to look at orthogonal complements. The orthogonal complement is basically the collection of vectors that's orthogonal to something, and that's more or less our first definition. So if U is any subset of V, our inner product space, and here you notice this is a subset, so this is not necessarily a subspace. That's not required. It often happens that way, but doesn't need to be. Then the orthogonal complement of U is this dealie here, U perp, and it's defined to be all the elements of V which are orthogonal to everything in U. Oh, sorry, I just realized that this is, I did that wrong. That should be for every element of U. So it's the V's that are orthogonal to everything in U. All right. And so then we have some basic results about how this works as an operation. The properties of perp. What happens when you take the perp? So first off, we have that if U is contained in V, then then the orthogonal complement is always a subspace of V. Even if U isn't, U perp will be. We also have that the set of things orthogonal to 0 is the entire space, and the things that are orthogonal to all of V, well, that's only the 0 vector. And if you look at the intersection of U with its orthogonal complement, the only thing that satisfies that is 0. The reverse, I mean, this is an equality here, actually. This is equal. It's just that the containment that I wrote is the only one that's non-trivial. The other one's obvious because, well, we just said that U perp is subspace, so it definitely has to contain 0, right? And then what else? Oh, and then we also have the fact that it reverses containment. So if you have U is a subspace of W, then W perp is going to be a subspace of U perp. Okay, and let's see about proving a couple of these. So for the first one, okay, so we've got the 3 things to check. So first of all, 0. 0 is definitely orthogonal to U for anything, and in particular all elements of U. So that tells us that 0 is going to be in U perp. We have, let's see, so if we check additivity, we're going to need to pick a couple of things from U perp. Okay, so then what does that mean? That means each one of them is orthogonal to everything in U. And now we need to check that if I take their sum, that will be orthogonal to anything in U. So maybe I should say then, if we take something from U and we put it in the inner product with the sum, well, I bet you can think without straining yourself too hard about what we need to do next. And the only thing we can do is use additivity in the first slot. So when we do that, we get V against U and W against U. And then our hypothesis was that this is equal to 0 and this is equal to 0. That's the significance of this one right here. That's our hypothesis. So this whole thing is equal to 0. Okay, and so then that gives us that V plus W is orthogonal to U for everything in U, and so it's going to be in the orthogonal complement. And of course we also have to check scalars. So if we take our favorite scalar lambda, then when we throw lambda times V in there with U, and once again, there's not a whole lot of thinking to do before you see that you can pull out lambda. using the linearity in the first slot. And then again, by hypothesis, this inner product is equal to 0. So then 0 times lambda is 0. And then that shows that we have lambda v is orthogonal to everything in U. All right, so no surprises there. B and C, I'm just going to claim that this is a restatement of what I called 6.12 plus. My sort of strengthened version of 6.12. And I claim also that D is immediate from 6.12 plus as well. You can look through the details if you like. The book has a nice description of it. And then finally, let's see. So if we take W to be in W perp, then in order to get this implication right here, we need to see that W is also in U perp, right? Okay. So let's see. So then, oh, actually, you know what? Let's call it V because it's not actually in W, so that might be confusing. So take V to be something from the orthogonal complement. All right. So then that means that VU in inner product is 0 for all U's in W. And since W includes U, right? So our initial assumption right here was that, you know, here's the vector space U, and it's sitting inside some larger vectors, well, larger or equal vector space W, right? So if V is orthogonal to all of this, then in particular it's orthogonal to all of this as well. So since W includes U, we have that V is orthogonal to U, which puts us in U perp. Cool. Okay, so that wraps that up. The end.